No, absolutely. I think that's why I always present many different ways of
So much for the 4 o'clock. Hi everybody, and welcome to today's CFA Colloquium. Our speaker is Ben Shappee. Ben was an undergraduate at Rutgers before he completed his PhD at Ohio State University, where he worked with Professor Chris Stanek and Chris Kochanek. Ben's now a Hubble and Carnegie Princeton Fellow at Carnegie Observatories in Pasadena, where he's interested in both observational and theoretical astrophysics. Some of the topics that he likes to work on includes optical and time domain surveys, type 1a supernova progenitors, which we heard about at lunchtime, Cepheid distances, and dynamics of few body systems. But today he'll be telling us about the all-sky automated survey for supernovae. Take it away, Ben.
Thank you very much, Matt. So today I'm going to tell you, as Matt just told you, about ASASIEN. This is a project that took up a decent chunk of my thesis and has really started to yield dividends lately. And the project has grown immensely. And what I hope to convince you of in this talk is that ASASIEN isn't just useful for finding the nearest and the brightest supernovae on the sky, but is also can be used to address many other areas of astrophysics, and especially in transient astronomy. And so the first thing I just want to bring to your attention, which of course we all know, is that the sky is quite large. But if you want to put a single pixel on every square arc second of the sky, and then do a transient survey this way, you end up with about a terabyte of data for every epoch that you want to take. This is not insurmountable, but it is a challenge that has to be met. And there's different surveys that meet this challenge in different ways. And the approach that ASASIEN takes might be different than Pan-STARRS, which you're probably more familiar with, and that we use very large pixels, and that actually decreases the data rate that we obtain. But it does mean that we only observe brighter sources. But the sky isn't just big. It's alive, it's vibrant, it's variable. Sometimes it's even violent. There are many different objects on many different scales that change in the sky, and this is why I love transient astronomy so much. You're always working on different objects. So there's objects in our own solar system, like asteroids and comets, to our own galaxy, like stellar eruptions, and all the way to extragalactic events like supernovae and AGN. And a transient survey like ASASIEN can be used to address science in all of these areas. And so this is kind of gives you motivation to sit through the next hour, and basically I want to tell you our goals and give you a hint that we're already starting to meet them. So the main technical goal of ASASIEN is to monitor the entire sky every few nights down to a V-band limiting magnitude of about 17. To do this, we use commercially available telephoto lenses and CCDs. The reason we do this is because it's twofold. The first, it makes it less expensive. ASASIEN is relatively cheap compared to other surveys like Pan-STARRS or ZTF or LSST in the future. But it also allows us to quickly expand as more funds become available, as it already happened multiple times in our history. So we can expand in the course of months as we get more funding, rather than years or multiple years or even decade timescales that larger, more traditional surveys would take if you have to build your own optics. But the prime scientific goal of the ASASIEN survey is to find supernovae, nearby supernovae, with a minimally biased search as possible. And this drives many of the decisions that we make as far as our survey cadence, our sky coverage throughout the survey. And you'll see this come up again and again. And the bottom plot here, I hope to convince you that we're already doing quite a good job of this. On this, I'll walk you through this plot. It's a little complicated. This is all the bright supernovae, brighter than 17th magnitude, that was discovered between May and December of 2014. And May of 2014 is when our southern unit went online. So this is when we became all sky. On the x-axis, I show you here the host galaxy magnitudes in the infrared. So it's just a proxy for mass. So large galaxies are on the right, small galaxies are on the left. On the y-axis, I show you the offset of the supernova from the center in arc seconds. So right at the center is down here, and then 100 arc seconds is at the top, so way out on the outskirts. And I break down the supernova by who discovered them. So in black triangles, I show you supernovae that were discovered by amateurs. The red circles are supernovae that were discovered first by ASASIEN. And then the blue squares are the supernovae discovered by all other professional surveys combined in this time frame. And there's three things I want you to get from this plot. The first one is that ASASIEN is doing quite well. There's a lot of red on this plot. The second thing that I want you to get from this plot is that ASASIEN, because we're all sky, we don't just find supernovae in big galaxies. We find them wherever they go off. So we find them in big galaxies, and we also find them in small galaxies. You can actually see that our fraction of discovery is actually extremely high at the smallest galaxies. And the last thing I want you to do from this plot, which is probably the biggest surprise a priori, is that these dashed lines actually represent the median offset of these supernovae from the centers of their host galaxies. So what I told you, ASASIEN has these very large pixels, so you might think that we do very poorly at the centers of galaxies because we have a whole bunch of galaxy light that are contaminating us, and that you have to see the supernova through. But you can actually see, just from these medians, that we're basically a factor of 2 better than all other professional surveys combined, and we're a factor of 4 better than amateurs. And amateurs may not be surprising, but it is surprising that we do better than professionals. And we do extremely well at the cores of galaxies. Our median supernova is basically 1 pixel, within 1 pixel of the center of the galaxy. So our pipeline, which took 2 years to develop, works extremely well even in these crowded regions. And this is another theme that will kind of weave itself through this talk as I describe some of the other transients that we've discovered. So the collaboration of ASASIEN has really grown. We're definitely a global partnership now. Here, I just wanted to highlight the builders, so the people who work on the survey day to day, and also the people who have invested time in the pipeline. So myself and Chris Kachanik wrote basically most of the pipeline together. Our grad student, Tom Holoin, who you guys should definitely invite out for a lunch talk if you get the opportunity. He's extremely good, has also been working on the pipeline as well. And Tom has had a number of papers from ASASIEN sources, so his name will come up over and over again in this talk. Jose Prieto has been an integral team member for the entire time of ASASIEN. And finally, Chris Stanek is our PI. If you want to break it down by institution, where everything is done for ASASIEN, Ohio State University, where I got my graduate degree, is really the home base. It's where the scheduling is done, it's where the data is downloaded, it's where the pipeline is run. It's really the heart of the ASASIEN survey. LCOGT is also a key member of ASASIEN. They supply our site support and our mounts, and I'll talk more about them in the next slide. And finally, Los Alamos, University of Warsaw, and the University of Católica are in our pipeline. Our funding comes from these sources. We just recently got awarded a bunch of funding from the China-Chile collaboration. And then finally, ASASIEN just tells you that a particular part of the sky has gotten brighter or fainter. And so you need a huge number of follow-up resources to actually figure out what these objects are and learn more about the astrophysics with these objects. And that's a huge number of institutions have supplied follow-up resources, including, of course, Carnegie Observatories, where I am now. So LCOGT is a global network of 1, 2, and 0.4 meter class telescopes. They supply our site support and our mounts, and the two sites of theirs that are important for ASASIEN are Haleakala, Hawaii, and Cerro Tololo, Chile. Our first unit, which is named Brutus, which went to Haleakala, Hawaii, it shares a dome with the Folks Telescope North 2 meters, shown here. It's in a clamshell dome, so it opens completely up to the sky. You can actually see us right there. We're in the background. If you zoom in on our first unit, this is Brutus. It looks kind of funky, so I'll kind of walk you through. It's different than what you might be expecting. We have 4 14-centimeter Nikon telephoto lenses. They're backed by 2K by 2K thermally electrically cooled CCDs from Finger Lakes Instruments. These are just advanced amateur cameras. There's 4.5 degrees on a side for the field of view, which gives us a pixel scale of about 8 arc seconds per pixel. We run V-band filters. We don't run clear like many other groups. Our limiting magnitude is actually set by lunation, so it depends on how bright the moon is, because our large pixels mean that we're sky dominated. And so it changes between about 16.5 to almost 17.5. This one unit can survey 10,000 square degrees per night. We first got our first 2 cameras in December of 2011, just for scale. And then the next 2 cameras came at the end of 2013. And the time in between was really using the original data to build our pipeline and improve many different things. That's just another view. This is an example of data from Brutus. The 4 cameras are splayed. There's a 1/2 degree overlap between them. Along the edges in other fields, we also have a 1/2 degree overlap. And this means, since the edge of these fields are quite large, about half the sky actually has twice the cadence that I typically consider the cadence for ASASIEN, because they're in between 2 fields. So that's just something to keep in mind. This is the size of about the full moon on these images, and that's the entire field of view of LSST. So you can see this is a huge area of the sky that we're surveying in every snapshot here. Our southern unit is in one of the OG1 structures from LCOGT. This is one of their 0.4 meters. If you flip it around and go inside, this is Cassius. It's the same as Brutus, except it first got its first light in May of 2014, and then we completed it and put 4 cameras on it in the mid-2015, mid of last year. This is our typical sky coverage in Cadence. This is the entire sky. I just pulled this off from one of our status web pages yesterday. The black are fields which are going to be observed, or which were observed last night, or at least scheduled to be observed last night. And then the color coding is the other parts of the sky and when they were last observed. So you can see that we cover the entire sky basically every 2 days. We just started doing the Southern Galactic Plane last dark time, so we now have reference images on this side, and this dark time will build reference images on the other side. And at that point will be the first transient survey in human history, at least to my knowledge. The military might have something, looking at the entire 4 pi, or at least the entire visible part of the sky for transient events. Of course, we avoid the moon. We can't avoid the moon, and this is just the daylight section in case that's the sun. If you want to look at the number of images that we take at each location in the sky, this is the past year in ASASIEN. So you can see that we just started building the Southern Galactic Plane. And you see that in portions of the sky, we have between 180 to 270 images in a year at a particular location of the sky. And then this will just start to be filled in as soon as the moon is new. This is the ASASIEN pipeline. I don't want to go through the details. I don't want to bore you and put you all to sleep. But there's 2 main ways that we make data public. The first one is through our human scanning, and this is our transient source detection pipeline, which looks for new sources that were previously not there. And the second way, which I'll talk about right now, is our ASASIEN patrols. And so these are an organized way to release our data and make it public. We're still getting them off the ground. We've started with the CV patrol, and what this does is it looks for known sources for interesting behavior. So we monitor all the bright CVs on the entire sky. You can go on the site and you can just see what our light curve of that object looked like for the past 4 years if it's in the north. But beyond that, the idea of this is that they're organized, focused, and useful. And these are not easy words to actually meet. And they're definitely organized and focused. But to be useful, especially for CVs or other objects, we thought we had to do a little bit more. And here, what we're doing is you can enter your own criterion. So if you want to know if a particular type of CV is in outburst, you can go in, you can make your own alert. You can set up your own parameters, what part of the sky you want, what magnitude you want it to be flaring by, what type of CV. And then it just sends you an email basically an hour after our data is taken. So we take data. If that object is an outburst, it should send you an email basically an hour later telling you that, hey, you might want to look at this object. So it's useful to the entire community. We started with CVs just because they're easy and isolated. We're thinking about going on to M dwarfs, basically every M dwarf in the sky that's brighter than a certain magnitude. We might limit it and do basically any M dwarf with an SDSS spectrum. So then you can know more about the object when it's outburst. Then expand on to quasars, blazars, and AGN. And we're open to suggestions as well. Please don't hesitate to ask if you have a particular type of source that you think deserves a patrol. We can talk about it and see if it's feasible to do. And so now for the more exciting new sources that we found, these are probably most of our exciting discoveries so far have come from this pipeline. And it's an image subtraction pipeline, so you get a bunch of images, you build a nice deep reference image at a particular location in the sky. You then get a new image at that size, so this is the reference image. You then have to interpolate it so it's on the same grid. Then you can volve the reference and then subtract. And basically all of the constant flux should just go away. And this is actual ASASIEN data for the LMC. So you can see the LMC just completely disappears. And then you want to look on these subtracted images to find new sources. And to do that, we use sex tractor. So we basically identify new sources, either getting brighter or fainter in the subtracted images. But now you're hugely false positive dominated. So there's many cuts that you have to go through to actually whittle this down to a reasonable number of sources. And this is what took actually 2 years of work, was really just this one bullet point. But now it's working. This is what our typical scanner will see right here. So at this location of the sky, this is the reference image. This is the subtracted images co-added for our dithers marching through time. And you see there's nothing at this location. You can see right here there's more noise. That's due to it was bright moon. And then finally in this top row, you see there are 2 dithered images at this location, a coed of that, and you see we easily recover the 16th magnitude asteroid. And so this is what we don't scan asteroids. Pretty much all the asteroids that ASASIEN sees are already known, so our scanners don't look at them, but this is just to demonstrate what they typically see. Oh, and the other thing that I should mention on this slide is that transients are typically discovered and announced in hours, and this is an important part of ASASIEN, is that we're very quick, or we at least try to be, and this will come up a couple times throughout the rest of the talk as well. So like I said before, we have to use a huge number of follow-up resources to follow up ASASIEN sources. We use the LCUGT 1 meters heavily, and we also use a huge number of other telescopes as well, including the Swift Space Telescope is extremely important for ASASIEN, I think, basically any transient astronomy at this point. It's really a UV spacecraft that you can actually get time on relatively quickly and actually get quick turnaround. So I can't stress enough just how important Swift is to many of our discoveries. And so we've had many discoveries in ASASIEN. We have 16 publications so far. I was just trying to count, but it's actually getting hard to count because there's too many papers being written. So it's about 10. There's probably more that I didn't count, which are actively being worked on now. We have hundreds of ATELs releasing our discoveries. It's a goal of ASASIEN to basically make our discoveries when we find a new transient as public as fast as possible. So once we're confident of something, then we try to write the ATEL as fast as we can. So then other people can also start to observe our sources as well, which is exactly what we want. We have, well, actually, this number's wrong. We had one more this morning, so 302 supernovae. The one this morning is a type A, so you can see the distribution there. The distribution on the sky is shown here, so you can see we're quite uniform in the northern and the southern hemispheres, although we don't discover very many in the galactic plane as you would expect. This is just an example of where the supernovae that we discover are in their host galaxies in a random sample of our supernovae using SDSS pre-explosion images. These are organized by the 2 mass magnitude. So big galaxies are on the lower right, small galaxies are on the upper left. So you can see that we find supernovae all over the place. We find them in the outskirts of small galaxies, the centers of dwarfs, and we find them at the centers of large galaxies as well, so all over the place. If you want to break down who's discovering supernovae, I sort of hinted this on my second slide already. These are the supernovae discovered between May and November of 2014. You can see that we're discovering about half the supernovae. But then if you look this year, we're actually doing even better. We're currently discovering a little bit less than 2/3 of all the bright supernovae discovered on the sky. But then it's a fair question to ask. You say, fine, ASASIEN is the first to discover these supernovae. But are you stealing these supernovae from other groups in some way? Basically, you're just discovering these slightly earlier than they would have been discovered otherwise? Or are you, possibly more interesting, especially for rates, are you discovering supernovae that would have been completely missed? Early is good. I mean, it's very important for a number of physical questions. But are we actually improving the completeness of the local supernova sample? And that's what this slide this is designed to show you. So this is a little bit weird. It's in days since June 1, 2013. This is basically when our real-time pipeline went on for just the northern unit. And before that, all the supernovae that are discovered by other groups that are not ASASIEN are in blue. Supernovae that are discovered first by ASASIEN are shown in red, and the supernovae that are found by other groups and then later seen in the ASASIEN data are shown in green. And we're not trying to take credit for these. We're just showing the ASASIEN completeness by these green bins. And this gray band is the 1 sigma deviations for times before we turned on our real-time transient pipeline. So what you can see is that in the first couple months, even the first year, we really didn't do very much at all. We're still working on improving the pipeline during this time. But then we got much better. And you can see for the past year and a half now, we really are adding to the completeness of the local sample. Many of these histograms are significantly about 1 sigma above what they would have been otherwise. So a large fraction of the supernovae that ASASIEN's finding just simply would not have been found without ASASIEN, even though they're extremely bright nearby and can be easily studied with 1 and 2 meter class telescopes. You can see that we're also very complete. The vast majority of these supernovae that occur, we recover, but we do have some room for improvement. And we are constantly improving our pipeline and getting better and better and better. And I strongly think that the best is yet to come. If you want to know how our completeness goes as a function of redshift, that's what this plot is designed to show you for supernovae. So going into the Hubble flow, so you can't really pay attention down here. But this shows you the cumulative distribution of supernovae that are discovered by ASASIEN as a function of redshift. And this dashed green line shows you z cubed, so volumetric. And what you can see is that between 0.01 and about 0.02, we're basically complete, totally complete. And then beyond 0.2 to about 0.02 to 0.035, you can see that our completeness drops off. So we're not very complete in this region. It tails off. But we are almost completely complete within a redshift of 0.02. So now I'm going to talk about some specific examples of ASASIEN discoveries or types of transients that ASASIEN has discovered. The first one I'm going to start off with is ASASIEN 14LP. This was a 1A that was discovered in 2014. It was the second brightest supernova in 2014. And what's interesting about it is that we discovered it just 2 days after explosion. And discovering, for those of you who saw my ITC talk, discovering supernovae, the lunch talk, discovering supernovae early is very interesting because you can constrain progenitor systems this way. There's still, with 1As, there's still this uncertainty on whether the majority or all supernovae come from a double degenerate scenario where you somehow merge two white dwarfs together, or a single degenerate scenario where you accrete material onto a white dwarf until it reaches roughly the change of sacral mass and explodes. This uncertainty still exists, and it's quite embarrassing, especially how heavily we rely upon these objects as tools in astronomy. If you discover a supernova early enough, one of the tests for distinguishing between these two classes of models are, do you see interaction with a companion that's nearby? So if there's a non-degenerate companion that's feeding onto the white dwarf, it has to be extremely close. It has to be overflowing its first lobe. And then when the supernova ejecta comes out, as this artist's picture shows, the ejecta is going to strike the companion and create a shock on the companion. And if your viewing angle is not unfavorable, if the ejecta doesn't block your view of the shock, then you expect extra light at early times in the light curve. So if you can discover supernovae extremely early, then you can see this extra light. And this is work by Dan Kaysen. It's a well-cited paper, showing in different filters just how much extra light you should expect given different companions. And so you can see if you can discover it very early, you can distinguish between these models of just a supernova rise and additional light from this impact. And so, but to do this, you actually have to know when the supernova exploded. So how do you figure that out? Well, it's two main methods. The first one, which is the more common one that's used, is that you take the very early time light curve. So if you look at this portion of the light curve, and you fit power laws to the early time light curve until you get zero flux. And the slight difference I did in this study is I used all the filters and I just allowed them the power law index to be different, but I forced them to all have the same explosion time. So that gives you an estimate of the explosion time right here. And this is a good figure to show that while we did discover this, the supernova 2 days after explosion, we actually had an epoch the day before. The reason we didn't discover it there is because it was cloudy. So the data was poor, which is unfortunate. But when we go back in that data, you can actually get a decent photometric measurement less than a day after explosion. So this helps you even more. And then you can look to see if you see any interaction in this very early time light curve. There was also some amateur data that was likely taken to the same galaxy. Koichi Itagaki, he's an extremely good supernova hunter amateur. And so that data is also constraining too. So then that helps you constrain an explosion time. Another way to constrain when this object exploded is work that's done by Tony Piro. And basically, he showed that you should expect lines, the velocity of lines, to change in a very particular way since explosion as a power law. And so what you can do is you get this amazing spectroscopic time series for this object. Because it's so close and bright, you can get a huge amount of data. Then you fit for silicon and calcium lines. And you find just how fast they're moving, and then you vary the explosion time until these power laws fit this data very well. And this is a good time to point out that a number of the data that we got for 14LP came from the Fred Lawrence Whipple 1.5 meter. And these are extremely important observations to help constraining the explosion time. And so now we have two estimates of the explosion time. You would hope that they would agree. In a number of supernovae, including this one, they don't agree. So then you have a range of explosion times that are possible. So that means when you're looking for this extra flux at early time, you have a number of different times that you could put in this flux. And that means that your constraint on the radius of a possible companion changes with time. That's what's shown on the right-hand side here. So as a function of explosion time, what's the maximum radius that a companion could possibly have? You can see that our observations, if for certain explosion times, are extremely good. So if it's closer to the spectroscopic explosion time, the radius of a couple tenths of a solar radius, or all that's allowed by our data. But if it's a later explosion time, significantly larger companions can be there. And this emphasizes a couple things. One, that we want to increase our cadence for these types of surveys. And two, you really don't want to be affected by weather. You want to go to multiple sites so that it's not cloudy on multiple sites. And you can make sure that you discover these very early. This then leads into the question of just how early could ASASIEN have discovered the supernovae or other transient surveys. And so just taking my fit power law to the ASASIEN V-band light curve, you can then ask the question, roughly, how early could different surveys discover the supernova? And so you see that ASASIEN could discover the supernova about 10 to 12 hours after explosion. That's the earliest it could have found it. PTF could have found this basically 2 to 3 hours after explosion, and LSST could find it almost instantaneously. And one common misconception that I continuously run into is that I'm constantly told, is like, oh, what is ASASIEN going to do once LSST is around? Because LSST is going to find all of your transients when they're far too faint for you to possibly find them. But the problem is that this is just not true, especially for the brightest nearby sources. Cadence is king. None of these surveys have anywhere near a couple-hour cadence. So it doesn't matter if LSST can go significantly deeper than us. If their cadence is too short, then we'll still find them almost all the time. That's one of the things I want to emphasize in this talk, is that cadence is king as far as bright nearby transients are currently by all transient surveys. Current surveys, this is the limiting factor for finding these bright objects as early as possible. The next exciting ASASIEN source that I want to talk about is ASASIEN 15LH. This received a decent amount of press recently, a little bit more than I was expecting. And this is what we put forth as the most luminous supernova ever discovered. On the right-hand side here, I show you the archival DECAM image. It went off in this pretty large, well, you can't tell it's large, but it's definitely a red galaxy. And in the bottom, I show you the LCOGT follow-up. So you can see that it's very blue. You can see. And this is a little bit of an interesting story about how it was discovered. It was in ASASIEN data for a reasonably long time, including even through peak. The black points here are the peak of the light curve, or the ASASIEN light curve. But it wasn't until we went into dark time that we actually triggered on this source. And then when we went back, we could then see that it was in ASASIEN data for a while. So we saw this light curve and we said, oh, it's probably just a normal supernova that we've had for a while. That's unfortunate that we didn't catch it earlier, but what are you going to do? So then we got spectroscopic follow-up, and this was the DuPont spectra that Nidia Morel from Carnegie Observatories took for me. And it looks nothing like any of the hundreds of supernovae that we saw previously. And actually, Subo Dong looked at this spectrum with Jose Prieto and said, oh, it looks kind of like a superluminous supernova, but then that would have to be at a redshift of 0.23. They actually but just moving the spectra back and forth to fit this this line that's commonly given to be oxygen absorption. And they say, oh, if that's true, then this is an extremely luminous, superluminous supernova. It's much more luminous than the previous ones. We don't believe it, but we need to get follow-up data. We had many mishaps trying to get data. They used the wrong slit angle, so then the blue part of the spectrum to get the magnesium-2 lines went off. We had weather, we had ice. We had the wrong grading put in once, so we missed the blue another time. But finally, my undergrad advisor, Saurabh Jha, was able to get a spectrum on the magnesium-2 lines, put it out of redshift, almost exactly what Subo just did by eye, which made this twice as luminous as the previous most luminous supernova ever discovered. And then we SALT telescope. And that's actually isn't the one he got. He got a couple days earlier. But which showed hints that yes, the magnetic followed it up just a couple days later on the Clay telescope, and Ian Thompson, again from Carnegie Observatories, took this spectrum for me and confirmed that yes, it is at this redshift, and we have the right luminosity. And so when you compare this to previous superluminous supernovae, you can actually see that it's a factor of 4, roughly a factor of 4 brighter than the previous most luminous type 1 superluminous supernova, which it is. It shows no hydrogen, no helium in its spectrum. The exact nature of this object is still reasonably uncertain, but because it's so bright, we can get a huge amount of data on this object, and we're continuing to get data on this object. And you can compare, so you can fit a black body to the multiband photometry. You can get a temperature. You know its luminosity, so you can get a radius, and so you can see for this object that just like other supernovae, it gets cooler with time and it's expanding, just like any other supernova explosion. And while the nature is still a little bit uncertain, because previous models to describe type 1 superluminous supernova use a magnetar. So in a normal core collapse supernova, you collapse down to a neutron star, and in these particular supernovae, it's thought that you have a rapidly rotating neutron star with a very strong magnetic field, so you can tap into that rotational energy to get an additional source of energy to power your light curve. The problem for this particular object is that it's right at the boundary. You can only spin a neutron star so fast before it breaks up, and this is right at the boundary of how much energy you can imagine getting out of this model. So it's a little uncomfortable of a place to be for that model. So it's not clear if this is a completely different type of object. It's in a different type of host galaxy than the other superluminous supernovae. Maybe the magnetar model can explain all of them, maybe explains none of them. This is still definitely a story that you should stay tuned to going forward. We have HST data on this object coming. We're still following this in the UV all the way through the optical, so it's quite an exciting object. Moving on to more galactic sources, as we'd heard during the ITC lunch, maybe some people aren't interested in CVs, but I disagree. I think many people are still very interested in CVs. We found hundreds of CVs that we make public. Some of them have tens of thousands of observations from professionals and amateur astronomers. We find a couple outbursts from young stellar objects. So these are very young stars with an accretion disk around them. We see a very large outburst from these objects, and it's thought to due to basically increasing the accretion rate in their accretion disk. And what's particularly interesting here is that we saw this large outburst. Tom wrote a paper describing it. But if you look in the CV patrol now, as I show you on the right-hand side, it's not a CV, but we put it in anyway. And you see this is this original outburst, but now it's even in a higher state. So if you had been interested in this object and you signed up, we would have told you right when this went, you would have known right when this object went into this even higher state. The spectra of these objects are quite interesting. They just show just a huge forest of emission lines, mostly iron, and titanium emission lines, and they're quite funky objects. Going on to stellar flares, ASASIEN's actually been quite productive in discovering large stellar flares. So we've discovered 43 M-dwarf flares that are larger than 4 magnitudes. We have the 2 largest M-dwarf flares ever detected, at least if you consider that as a function of the change in the V-band magnitudes. So they're both more than 9 magnitude flares. And we even just recently discovered a 10 magnitude L-dwarf flare. And so M-dwarfs are, of course, interesting for a number of different reasons. They're extremely common objects. They're fully convective, and yet they still are very magnetically active. And there's interest, especially here, about planets around M-dwarfs and the possible habitability. So 6% of M-dwarfs are thought to have an Earth-sized planet in their habitable zone. This is interesting, but it's not immediately clear if you're a habitable world around one of these M-dwarfs and you go through one of these huge flares, what exactly happens to you. So it'd be very nice to know roughly what the flare distribution of these very large flares and these late type M-dwarfs are. And that's one thing that ASASIEN can start to address, can start to help to address. So This is the first large M-dwarf flare that we saw. This is a 9 magnitude M-dwarf flare. I already mentioned it. This is the light curve, and this is kind of the story of this discovery can basically tell you how quick things can happen in ASASIEN. So we triggered right here on an outburst. We went through human scanning. We saw what it was. We saw there was archival SDSS data at this location. And so we figured it was a huge M-dwarf flare. And then we quickly turned around and actually rescheduled another observation on the same telescope in the same night. So just 2 hours, a little over 2 hours later, we got another observation of this source. And so then when you split our two different images separately, you can see that in 100 seconds, this fell by half a magnitude. And then it fell by basically 4 magnitudes, a little over 3 magnitudes in 2 hours. So then you can fit obviously rough, flare models to these photometric points, and you can compute how much energy actually, how large this flare was. And the equivalent duration of this flare, which is a measure of how long would it have taken this object to emit this amount of energy that you saw in the flare, in quiescent phase is actually 3 months. So this object released 3 months worth of its normal luminosity in just over 2 hours. And I think any habitable world nearby would not have been very happy after this. The L-dwarf flare that we just saw, so this is work that's, so the previous, I should say, was written up by Sarah Schmidt, a previous Columbus fellow. Our current L-dwarf flare is still in progress, or at least the paper is still in progress. And the flare is done. And it's a 10 magnitude flare on what looks to be an L-dwarf. We have near-infrared spectroscopy. We have very deep optical spectroscopy. And of this flare, you can do the same thing where you fit models to the points. This time we couldn't reschedule any observations afterwards, but this was on one of these, half the sky where we have it on multiple fields. And so we did actually get an upper limit just a little under 2 hours before the flare. So you can constrain the energy of the flare quite well, or reasonably well. And you see that this is a huge, huge flare. The equivalent duration of this flare is actually 4 months, so it's even longer than the previous one. And I'll emphasize that this is only the second flaring L-dwarf that we've seen. So Kepler has seen one flaring L-dwarf. The flares in that are not nowhere near this large, and then this is the second one discovered. So the rates, why they flare, there's a huge number of open questions still for flaring L-dwarfs. And if you want to know the distribution of M-dwarf flares, what's typically done is you take a telescope, you point to a part of the sky, you find all the M-dwarfs in that portion of the sky, and then you ask the question over the next couple nights, how often do these stars flare? And then you can make plots like this, where as a function of spectral type, you say how often flares of a certain size occur on these stars. This works extremely well, but there is a couple problems with this. For very, very large flares, you may not be able to go deep enough to actually see the star that's flaring. So for the very large flares to the right of here, all of the ASASIEN flares are very far to the right of this plot. You just can't go deep enough to actually see what's flaring. So the difference between typical flaring rate measurements and the ones that ASASIEN can make are that our volume, instead of going deep in one portion, our volume is the brightest part of the sky. It's everywhere on the sky. And so if you have a flare that's in a region where you have pre-explosion imaging like SDSS or pan stars, when the 3Pi survey becomes public, you can immediately know immediately know what the object is. And if you can't see the object in the pre-explosion imaging, then you know it's extremely interesting because it has to be more than a 6 magnitude flare. So then you can go a little bit deeper and find the source. So ASASIEN can really start to push to the right of this, and we can also start to push to later and later M-dwarfs because our sample comes by, is very nearby, so then you can actually see these very, very faint stars that are flaring. Moving on to extragalactic science, we've seen many AGN and blazar flares in the ASASIEN data, and there's one particular case that I'm going to describe now, which is a flare from NGC 2617, which is a nearby galaxy. So just to give a teeny bit of background to refresh everyone's memory, there's a unification model which basically is used to describe the difference between type 1 Seafords, where you see broad H alpha, H beta, H gamma, and often, but it's not part of the classification, that you see this blue continuum. And type 2 Seafords, which you just see the narrow line emission, which you also see in type 1 Seafords. And the unification model describes this difference basically just as a viewing angle effect. So you have some obscuring torus, which is blocking your view of the central source for type 2 Seafords, so you don't see the hot accretion disk, you don't see the blue flux, and you don't see the broadline region. Whereas in type 1 Seafords, you do see the central source, but in both cases, you see the narrow lines, which come from ionization of gas at much larger radii. This is a very nice picture. I think it's really helped AGN astronomy. But there is one thing that's kind of hard to reconcile, and that's that a number of AGN have actually been seen to change their type over time. Actually, in this past year, it's become fashionable to actually look in SDSS spectra of quasars, and you actually see quasars changing both ways. So it's not just something that happens in low luminosity AGN, it happens across the luminosity range, and you can change your type. And there's even one example, Markarian 590, which actually in the 70s was a type 1 Seaford, a type 2 Seaford, went to a type 1 through the 90s, but then decided didn't like it and switched back in the late 2000s into recent times. Now it's a type 1 Seaford. So it's a little hard to put this together, and what's interesting in regards to this talk is that ASASIEN's actually been able to find one of these changing look AGN, which is, I know it's quite surprising. We're a small photometric survey, so how do we find a spectroscopic changing source? Basically, we triggered on a 10% increase of flux in the inner regions of this galaxy, of NGC 2617. And because all of our sources are bright, ASASIEN has almost 100% spectroscopic completeness for anything that we see that changes that we believe is real, and it was not obvious what the source is. So we thought this might be a supernova right at the center of this galaxy, so we got a follow-up spectrum. Nope, not a supernova. It's quite clearly a type 1 Seaford. But what's interesting about this is it's not just variability, because we also then went in the archive and we saw that this was quite clearly a type 1.8 Seaford. So it's almost a type 2 Seaford, except there's a slight broad portion to the H alpha emission. So it went through this dramatic change in its spectroscopic properties. We announced this via an ATEL, and we were just going to leave it at that and let the community take over, except the outpouring of support to continue to observe this source was quite strong. People were basically volunteering to give us data on the source, which never happens in supernovae. And so we decided, what the hell, I'll write a paper on this. And so we applied for Swift TRO time, and we followed this object. And we saw that our detection was back here, and it actually then went through an even larger outburst afterwards. And this outburst is all the way from the X-rays all the way through the near-IR. And when I was trying to piece this together, we have a change in spectroscopic type. We have this large outburst, and I was trying to figure out what the actual story is going on here. I noticed one very interesting thing. So if you look at the outburst of this object, and you start in the X-rays, you can see that as you go to longer wavelengths, that the flare starts in the X-rays and clearly goes to longer wavelengths. And correlations between variability of AGN in the X-rays going to long wavelengths have been looked for a very long time, but before this study, it was never convincingly shown, at least nothing you could see by eyes. You could just point to it and say, oh, look, it's going to longer. And of course, if you do a cross-correlation analysis, then you can see that, yes, you can recover what your eye shows you, and that the lag between the X-rays and the longer wavelength photometry is there, and it increases with time. But what can be causing this? The first thing that you think of when you think of an AGN flare is you might think of, oh, an increase in accretion rate. But that doesn't really make sense in this object, because if you're going to add more material to an AGN, you might expect that you're going to add it to the outskirts of the AGN disk first, and then have this perturbation propagate inward. But this is not what we see here at all, right? We see short wavelengths very earlier, and then long waves very later. So this isn't what we see. But what we do see is we see the X-rays. So if you take a model and you create a model where you just put the observed X-ray flux at a distance above the disk, you assume that accretion is completely steady state. Then you take these observed X-rays, you say they emit in 4 pi, they come down and they hit the disk, and you say they immediately thermalize and then re-emit. This naturally gives you the direction that we see, where you start your variations at short wavelengths and then go to long wavelengths. And if you do this model in slight more detail, but not much, you get these black lines. You take the observed light curve, and then you actually just get out with the proper scaling. These black lines, you see we qualitatively follow the data quite well. So you can see we reproduce the UV, we reproduce the optical very well. Infrared, we don't reproduce that well. We see that the time scale is roughly right, but this could just be due to dust reprocessing. It's not clear what's going on there. But I think we do far better than you might expect, given the simplicity of our model. And finally, at the end of the talk, I'll finish just discussing our TDEs. ASASIEN has a number of TDEs that we've discovered so far. That we've discovered the 3 closest and brightest TDEs discovered in the optical. I show you one on the right-hand side here. And what a tidal disruption event is that if you, as James, of course, knows very well here, if you pass a star too close to the center, the supermassive black hole at the center of a galaxy, you actually will tidally disrupt the star, you'll rip apart the star, and then you'll have these tidal streams come around, and due to gravitational or GR precession, will actually be bent, and then it'll interact with itself. The details of exactly how you'll get optical emission or other emission from these sources is still hotly debated. But there's more than enough energy in both the amount of material that you could accrete onto the supermassive black hole at the center, and also the shock that's created when the stream interacts with itself. And so, it goes. So ASASIEN has actually proved to be very good at discovering these objects. Again, this might be surprising because these are, of course, by definition, right, the center of their host galaxies. But as I showed you earlier on, ASASIEN does very well at the centers of galaxies. And we're actually have ended up being, it's quite clear that at least of the TDs that have been announced so far, ASASIEN is much more complete than previous surveys. We have a much smaller volume that we're surveying than larger surveys like PTF or PAN-STARRS, and yet we discover comparable or more supernovae to both of those surveys, or TDEs in both of those surveys. So we have the 3 closest and brightest out of about 12 to 15, depending on exactly what you count as a TD candidate. And because they're so nearby and bright, this is a recurring theme, is that we have a huge amount of data on these objects, and we can follow them up in more detail than you possibly could for their fainter counterparts. And what's interesting about our rates is they actually end up being closer, although it's still not consistent with theoretical expectations for how often you would expect TDEs to occur in galaxies. And so I show you the discovery image of the three TDEs right here. You see, of course, they're right at the center of the galaxies. You can also see just how large our pixels are as when you compare them to the SDSS data. And then I'll just quickly flip through basically the immense amount of data that we were able to obtain on these objects. We go all the way from the UV with the Swift Space Telescope to the NIR. We have great spectroscopic time series for these objects. And you can really start to then find differences between them. So when you have just a couple data points, it's very hard to get a good handle on what's going on with this class of objects. And all 3 of our TDEs are actually end up being their own little unique snowflakes. They all have their own differences, and it's not immediately clear, but it's by gathering a large sample, or at least a reasonable sample, of these extremely well-observed TDEs that we'll start to be able to really test models and constrain them. I stopped at 14 Li for a reason. This TDE has received a huge amount of attention, including a paper by Ido Berger's group on the radio emission from this guy, but it was detected in the X-rays, the optical, the UV, and the radio. There's a Nature paper on it, there's a Science paper on it. Neither of those are written by the ASASIEN group. We have our own paper. And this is exactly what we want. We want to make our discoveries public as soon as possible and allow the community to study these objects in a huge amount of detail. And finally, going on to our most recent one, this 15 OI was actually quite a unique TDE too. It decayed extremely fast, so it faded very quickly. And what you can actually start to do when you have a sample of these extremely well-studied objects is that you can actually start to compare them in detail and not just a couple points on each object. And what you can see is this is here on the left-hand side here. I show you the optical and UV luminosity of these objects as a function of time, so you can see how they decay. On the right-hand side, you can then fit for a temperature at each epoch. And we can do this because we have the Swift Space Telescope. These are very hot objects, so then you need the UV to actually be able to fit a reasonable black body. And what's interesting, and this is one of the characteristic signs of a tidal disruption event, is that the temperature actually stays flat, and actually one of ours even rises. So for 15LH, I showed you, and all supernovae or explosions basically expand and cool, where these guys either stay the same temperature or actually get hotter with time. And then when you use these two, you can then fit for a radius, a photometric radius, what the radius of your photosphere is. You can actually see that these guys get smaller with time as well. So they get smaller, the photosphere gets smaller and hotter with time, which again is very different than supernova explosions. Another interesting thing that you can do is you can use all the spectra that we obtained, and then you can say, given the full width half max, how wide are the lines? You can, and an estimate for the mass of the black hole, you can say, what radius is the line emission actually coming from? And when you do that, you can see that the line emission is actually coming from a much larger radius than the photosphere is at. And you can see that in a couple of cases, it convincingly expands with time. So what's producing your lines is actually expanding with time, even though your photosphere is decreasing. And so that's really all I wanted to talk about as far as the ASASIEN discoveries go. But then looking forward in ASASIEN and what we can do in the future, one of the things I really want to do is I want to expand ASASIEN. I want to go, we have 2 sites right now, which is doing extremely well, but I want to go to 4 sites, each with 4 cameras at least. This would allow us to do the entire sky every night, which is a good goal, but that's not actually my primary goal of wanting to go to 4 sites. The real reason I want to go to 4 sites is because you could be geometrically separated. These details don't really matter. This could be in China, for example, or this could be in Australia. But then the weather is uncorrelated. As anyone from Boston knows from last year, bad weather can be very strongly correlated with itself. And so I showed you this plot earlier, and this is the typical type of cadence that we're getting over the sky. But bad weather happens. And in August of last year, we actually had bad weather for a very long stretch in both the northern and Hawaii and Chile. And this just kills any transient survey, and you really, especially when you're going for completeness, this just hurts immensely. And it's a little scary looking forward when you think of surveys like ZTF or LSST and BlackGem, where these are all single-site surveys, right? They're all from one site. So if bad weather takes them out, there are no transients from there. So you can miss the brightest opportunities of the sky. So you really want to spread out to multiple sites. And actually, in the southern hemisphere, it's especially worrisome because it's not only that they're all single-site surveys, they're all in Chile. Basically all the current successful transient surveys and the planned large transient surveys are all going to be in Chile. So if Chile has bad weather, there is no transient astronomy basically in the southern hemisphere unless we expand ASASIEN. And so one thing that I didn't even mention in this talk at all, which is also a big part of ASASIEN, given our name comes from the original ASAS survey, which was a all-sky variable star survey. It didn't have any real-time component. It wasn't as large as ASASIEN. It was smaller, but still has many hundreds of citations because the variable star catalogs that it made were extremely used, and we go deeper, have a faster cadence. And so this effort is being led by Andreas Jordan at the University of Católica, but basically we're going to have a all-sky variability catalog and make it public for people to use. And then finally, it's a long-term goal of ASASIEN to make our data public, but not just make it public, but make it public in a useful way, as I emphasized with our patrols. And so what I really want to leave you with is that not just with the idea that ASASIEN has all these cool discoveries that are very interesting scientifically, but really what interesting scientific questions might you be able to address with ASASIEN data? And please let us know. And looking forward, what collaborations can we form to get even more out of this survey? And with that, I'll just take your questions.
I have a question about this eyeball classification.
Was
Where, you know, when you have to check by eye all the events. So 14 years ago, when I developed the first version of Pipeline for Master, this thing took a lot of effort. But you know, we were in Russia, in the country of free manpower. So here the question is, how many human hours do you spend on this process? And what fraction of your manpower does it represent?
That's a great question, especially for somebody who has been doing this. It's a lot less than it used to be, actually. So we used to take 2 digital images, we now went to 3, and this drastically cut down our false positives. And there's a bunch of milestones that we've had in the development of the pipeline that have really limited the amount of human power that it takes. One of them was the introduction of machine learning to actually identify real versus fake. So now we're only scanning, it depends on the night, depends on exactly, if it's cloudy then you have more sources, but usually a couple hundred per day. So it only takes a few team members, basically an hour to an hour and a half, on full nights with data under marginal conditions where we have more sources. So it's not a huge fraction of the effort anymore. Really, what takes a lot of more time than just going through and seeing if a source is real or not to your eye is really the part that's harder to automate, which is figuring all the other contextual information and then trying to figure out what you think the object is and then put it in the bins and think, oh, this should get spectroscopically classified, or what should we do about this object. So that is usually what takes up the majority of the time of our scanners. Our scanners aren't undergrads. Chris Stanek is actually the dominant scanner for us, and so I think this is part of our success is that when we see a source in ASASIEN and it's real, we have the experts right already there to make determinations and be able to react really quickly, not like call someone from Israel to call someone in California to wake them up and figure out what to do. You already have the person awake. So scanning is still a burden, but it's not a stumbling block anymore.
James.
So one thing that's a bit surprising to me for the ASASIEN TDE events is that you seem to catch them on the decay tails with maybe even 2 months of a gap in coverage where they're not actually being caught near peak. And have we just gotten unlucky, and do we expect ASASIEN in the future to actually catch TDEs on the rise?
So it's a good question. The one with a 2-month gap, that was actually just coming from behind the sun, so no group could do better with that particular source. We have been catching them on the decline. I think, so that leaves 2 more. I think this is mostly unlucky. If it's in our data, but it's bright time and it's near the magnitude limit, then we don't see it until the sky gets darker. Then you see it. Then you can go back and say, oh, it was there when you do force photometry at the location of the sky. So I think it's mostly basically just not being lucky for these sources. And for sources that are near our detection limit, it's because of how our pipeline works, it's a little easier to determine if something's been there for a while than if it's just a new source and right at the detection limit. So mostly unlucky.
Notice that you find a lot more 1As than other types of supernovae. Why is that?
So basically all transient surveys do this. They're just because they're so much brighter that the factor of 2 rarer they are than type 2s just don't matter. It doesn't matter, but it's not the dominant factor. So it's just that they're 2 magnitudes brighter than type 2, so the volume you can find them out 2 is much larger.
But if you then analyze it to see what is the frequency, let's say, as a function of how bright the background galaxy is, for example, do you see any difference from the kinds of population assessments that previous people have done, or are you just consistent with what they've been saying about your data?
So the whole goal of ASASIEN, like really the core scientific goal is to actually answer exactly this question, but do better than has been previously done. And so this is work that the first paper should probably be coming out in about a year from now. So I guess you'll have to invite me back in a year to answer the question thoroughly.
I'll be very interested to hear the answer.
I have some ideas, but could you expand on your decision to use the V filter? So for instance, there is a recent supernova Centaurus A, but covered by a ton of extinction. It was easier to see in the R band. So you might be biasing yourself towards those events.
So that's a great question. So the reason we didn't get the Centaurus A supernova was not because it was extinguished. It would have been easy to detect in ASASIEN data. But it was actually 4.5 arc seconds away from an insanely bright star. I think a 7th magnitude star, or 8th. Anyway, I 5th magnitude star, but it was a very bright star. So it was in the same pixel in ASASIEN. And that's just unfortunate. There's just not that many bright stars in the sky, especially on top of galaxies. So, I don't know, nature hates you sometimes. As far as the filter goes, I think in hindsight we should have not necessarily went with the V filter, but probably a G filter. Then have a little bit more square, a little bit more throughput. But actually, I think going to a bluer filter was a great idea. I think this is one of the reasons why we find 1As easier, or find supernovae at the centers of galaxies easier, find TDEs easier. These are all blue sources on top of red continuum, so galaxies are just fainter in the blue. Transients and explosions are typically hot, so they're typically peak in the blue, or even in the UV. So I think actually going to a bluer filter benefits you. Going to B, or especially U, would be expensive. So I think V is a very good is a good compromise.
It'd also be more drowned out by the moon, obviously, too. So there's a bit of
There is. That's true. The moon is slightly painful for us.
But because you want speed, you don't have the time to do 2 filters. That's the thing.
And that's just expensive too, right? So our only moving part besides the mount right now are the shutters, and they fail on us basically maybe once a year, just because we're taking so many exposures so rapidly. So any moving part that you want to that would be changing isn't very good. But the mounts, I will mention, the LCHT mounts are excellent. We slew across the entire sky in like 10 seconds. So actually slew time going across the sky just isn't that big of a deal. So if you did a bunch in one filter and you switched filters and then you went back, then there's not that much of a cost to do that. But
Just
it's another
4 in our filter.
if you have money to do it, then we will do this. This is some of the things we're talking about, is doing another ASASIEN unit at different wavelengths. This would be an excellent idea to do.
Any more questions for Ben?
What's the cost of the system?
So when it's all said and done, an entire unit costs under $500,000. The mounts, I don't know if I'm allowed to say how expensive the mounts are. I don't know if LCHT makes that public. But basically the lenses are a little over 10 grand each, and the cameras are 40 grand each. And so that's the majority of the expense, is just in those two components. Or a large fraction of the expenses in those two components. And then you have to build an Ogwan and the mount and actually deploy it. So it's not a trivial amount of money, but it's also not an overwhelming amount of money when you compare it to the amount of science that we're getting out of it compared to our competitors per dollar.
Okay, if we've got no more questions, then let's thank Ben again.